So
why put it in the home state?
Why? Oh,
Yeah.
I'll show you a picture of that. So what's okay? So we built a rather more modest version of what I just showed you. It's here. These are the photodetectors. This is the sort of xenon region. This was only about 15 kilograms rather than a third of a ton. And we ran this in Italy. In one of these, we kind of got stuffed back here. We weren't in one of those big halls I showed you, but it was actually, here it is, rather more modest affair. But actually, we did this experiment. This was about 2 years ago, and we saw nothing. But we were the world's best at seeing nothing, which I know sounds like a kind of Pyrrhic victory, but actually in my game, and after 18 years of seeing nothing, I can tell you, you still feel quite good about it. So you have to be, and this is going to sound a bit tortuous, but you have to be very good at seeing nothing in order to be sure when you finally see something that you really are seeing something, if that makes any sense.
Yes,
It
yes.
does, good.
Yes.
So, okay, so let me answer this question about the homestake mine, and then I can draw to a conclusion.
Has anybody ever really seen anything?
They have, actually.
Are they sure they saw what they
No.
think they saw?
Yeah, no. We can talk about that afterwards.
Okay.
But it does. To be fair, yeah, there are people that say they have seen dark matter particles. So this is a representation of man's incredible lust for gold. This is an elevation view, if you like, of the Homestake gold mine. This is the surface, and this is going down some 8,000 feet. So over a period of nearly 120 something odd years, they chased gold all the way down the seams, all the way down 8,000 feet. There are over 300 miles of tunnels in this thing. And in 2002, when the gold price was, I think, about $240 an ounce, Homestakes took the view that it was time to close the mine. And they shut up shop, and we said, look, we really like it as a physics lab. Oh, actually, it's a science lab. Science lab. Engineering, geology, biology, physics. And thankfully, it took quite a lot of discussion, but the state of South Dakota, and also a gentleman called T. Denny Sanford, who stepped in with over $80 million, dollars, $80 million. Sorry, you can tell I've been negotiating with the British funding agency this morning. I've started talking about pounds. I never usually do that. T. Denny Sanford, it was an amazing gesture, but he was very keen to see science, get into South Dakota, and that's indeed. This here it's extraordinary. In the 80s, they realized they had sort of extra crushing capacity, so they said, oh well, let's go and see if we can find some gold up here. So they just dug this incredible, it's extraordinary 300 meter rather, huge hole into the ground, sort of just looking for more gold. Anyway, so what we're doing is we're rehabilitating this, and we're well through that program of setting up a new physics lab, and the physics lab is in fact one that already has a great tradition. This is the Davis, what we call now the Davis Cavern, or the Davis Lab, and it's actually where a chap called Ray Davis, who back in the 60s had this brilliant idea of, if you put what I suppose we can refer to as a half a thousand tons, 500 tons of dry cleaning fluid into a tank, and you watch it closely enough, every so often you can detect one nucleus change, and it changes because of solar neutrino. So these are again neutral particles, but this time coming from the sun, happen to cause a nucleus to flip. And he watched this for tens of years, and every month he and his team removed about 30 new atoms of argon that hadn't been there the previous month. And that was the first direct evidence that there were neutrinos pouring out of the sun and interacting with the thing. So what we're going to do is we're going to reuse this cavern, which is of the actually that's Ray Davis taking a swim in the cavern. It was designed. This was genuine physics purposes. You flooded it in order to change the radioactive background, the radioactive environment. Although, as you see, it was Ray's sort of private.
He's swimming in dry cleaning fluid?
No, sorry. The dry cleaning fluid is actually, is actually inside the tank. I think he'd more than.
That's the xenon.
You'd get very wrinkly in that.
He shrank. He's kind of
Yeah. So this is the sort of modern incarnation of the physics experiment. We, rather than having a horizontal water tank, we've actually made the thing vertical so that we can drop, or rather lower gingerly, our detector, this 2-meter high detector, into the middle of the water tank. So that's really what we're going to do. And this is actually me from about 8 years ago, standing underneath Davis's old water tank. So
the reason for the depth is to get away from background radiation?
it is absolutely. Sorry, you did. I skipped that slide. Okay. The problem is simply this: you hold your hand out here on the surface of the Earth, and several cosmic rays are going through your hand every second. They're basically what's happening is high energy cosmic rays are hitting the upper atmosphere and turning into these incredible showers. I do have a picture I can show you later if somebody's interested. One of those sort of byproducts happens to be a thing called a muon, a cosmic ray muon. It's a secondary product. Something else hit the upper atmosphere and it was generated in the atmosphere, came around. We refer to them as cosmic rays, even though frankly they never traveled through the cosmos. They're atmospheric rays, if you like. But anyway, the amazing thing about them is, okay, so you're getting a few per second through your hand here. You could say, well, let's just go a little bit underground and that'll get rid of them. Well, actually, no. If you go a mile underground and hold your hand out, then you can get to the point where you're going to be waiting 2 or 3 years with a mile of rock above you. It's about 5 years for one of those muons to come through. That's the kind of level of suppression we want to reduce these fluxes by. If we do that, what it does is it turns out that it allows us to be sure that when we see something happen in our detector, as I say, we have to get very good at seeing nothing, so that when we do see something in our detector, sorry, this is me looking incredibly grumpy on a thing, but I was going to make a joke about that, but I kind of lost my pace. I must move to conclusion because I'm already way over. This is a photograph of a couple of my offspring that, as you say, I've made already, so I'm safe in terms of passing on this damaged material.
Well, they came on all right.
But this is actually at LAD. I'm sure most of you are familiar with it. But there are just a few. I know I've tried to probably pack too much into this talk, but let me just try to make a few observations. I mean, the first one is what I hope to have got sense is this 95%. Right, I'm so sorry. I'll buy you a new one if I'm breaking it. I'm sorry. It's not mine. Jen, I'm really sorry.
Save the xenon.
Is we are trying to wrestle with, and every time they have a big scientific national review, they always come up with this dark matter problem and dark energy problem as being one of the big top 10 questions that we're faced with. So it was the big question of the 20th century. Unfortunately, it's still a big question in the 21st century. I thought we were going to have it answered. As I say, when I joined the field 18 years ago, I thought we were going to have it all stitched up, within 5 years, and everybody down the pub after that. But no, 18 years later, we're still at it. But I honestly, I think, hand on my heart, can say with a combination of this Large Hadron Collider, what we're capable of doing with direct detection, a number of other techniques that I haven't talked about, we really are homing in on this. It might seem like the sort of modern equivalent of hunting for the Grail, but I really do think we'll be able to. If I stand up in front of you 10 years from now, the story will have changed a lot, hopefully in the positive sense. Okay, so that's the missing mass of the universe. Providing a cure for ignorance. Well, certainly, for the last 25 years in particle physics, we've been in a desert. When I joined in the 80s. We had the standard model, and we'd done a tremendous job of finding just about all of the particles for that model. And since then, we think that we know how particle physics works at higher energy scales, but we've yet to demonstrate it. So I hope that finding dark matter will also cure our problem in particle physics, which is how does particle physics work beyond the current rather arbitrary, successful but nonetheless rather arbitrary standard model. Then there's another thing, which is it is an